An electric circuit. A current will only flow through an electrical component if there is a voltage or potential difference applied across its ends. The voltage is supplied by a battery or power supply and is connected to the component by conducting wires, normally made of copper. The animation shows how a battery, bulb and connecting wires form a simple electrical circuit. Current. Electric current is a flow of charged particles driven around the circuit by the battery. This can be measured by an ammeter which is placed in the circuit. The same current then flows through the ammeter and the circuit component. They are said to be connected in series. Current is measured in amperes or amps, A. Conventional current direction. It is convention to assume that the current's charge carriers are positive. Therefore, the current flows from the positive to the negative terminal of the battery. This was the direction guessed by early experimenters and is called conventional current direction. Circuit diagrams are always marked using conventional current direction. Electron flow. Today, we know that the flow of current through a metal wire is due to negatively charged electrons. Metals contain free electrons in their structure. These electrons are repelled by the negative terminal and attracted to the positive terminal of the battery. Complete circuits. In order for the current to flow, we must have a complete circuit. This means that there can be no breaks in the connecting wires. If the wire is cut, no current leaves the battery and no energy is delivered to the lamp. Voltage. The potential difference, or voltage delivered across a circuit component, can be measured by connecting a voltmeter across the component. The voltmeter is said to be connected in parallel with a component. This means that they are connected side by side. Potential difference, or voltage, is measured in volts. It can be seen that the current through the coil increases as the voltage applied increases. For the voltages from 0 to 8 volts, the graph is a straight line passing through the origin. The resistance of the coil is constant at 2 ohms for currents up to 4 amps. The gradient of the voltage current graph is constant. At currents above this value, the coil starts to become hot. Vibration of metal ions within the wire increases, and the charged particles that make up the current find it more difficult to pass through. The resistance of the coil increases. This effect becomes more evident at 9 and 10 volts. As we have seen, the resistance of the copper coil is constant at 2 ohms, provided the temperature is constant. The experiment is now repeated with 2 further copper coils, B and C. A graph showing voltage applied to the lamp against current flowing is shown above. The gradient of the voltage current graph increases as the current through the filament increases. The resistance of the filament is therefore increasing. Larger currents cause the filament to become hotter, therefore increasing its resistance. A graph of current flowing through the diode against applied voltage is shown above. No current flows until the applied voltage exceeds 0.6 volts. The resistance of the diode up to 0.6 volts is very large. Beyond 0.6 volts, the resistance of the diode decreases and the current flowing increases rapidly. The diode has begun to conduct. The experiment has been repeated with the diode connected in reverse bias. As you can see, the diode will allow absolutely no current to flow in the circuit. We can say that the diode does not conduct when connected in reverse bias. The forward and reverse current voltage graphs have been combined and are shown above. Reverse bias voltages are shown as negative values. Diodes will only allow a current to flow in one direction around a circuit. They are used in rectifying circuits to convert alternating current into direct current. Light-dependent resistors, LDR. An LDR is made of a semiconductor material whose resistance depends upon light intensity. The resistance of a light-dependent resistor depends upon the intensity or brightness of the light incident on its surface. The intensity of the light striking the LDR can be reduced by dragging pieces of tracing paper between the lamp and the LDR. The graph shows how the resistance of the LDR changes as the number of pieces of paper is increased. The resistance of the LDR increases rapidly as the light intensity decreases. LDRs are used in light meters and in light-activated switching circuits. Thermistors. The resistance of a thermistor depends upon temperature. Thermistors are made of a semiconductor material whose resistance changes as its temperature is changed. The temperature of the thermistor can be increased by raising the temperature of the water in the beakers. Observe how the resistance of the thermistor changes as the temperature increases. Above you can see a graph showing the resistance of the thermistor against temperature. The resistance of a thermistor decreases as the temperature is increased. Thermistors are used in temperature switches, temperature sensors, and thermostats for central heating systems. The factors affecting the resistance of a metal wire. The resistance of a metal wire depends upon its length, its cross-sectional area, and the type of material from which it is made. The ohmmeter measures the resistance of the length of wire which is connected into the circuit. Observe the change in resistance as the length of wire increases. The resistance values shown in the table include the resistance of the crocodile clips and connecting leads. The factors affecting the resistance of a metal wire. Thickness. If the thickness of a metal wire is increased, its cross-sectional area will also increase. Doubling its thickness will increase its cross-sectional area by a factor of 4. This increase in the cross-sectional area will change its resistance. Observe how changing the thickness of the wire changes its resistance. The graph above shows how the resistance of the wire changes as the cross-sectional area is increased. When the cross-sectional area of the wire is increased by a factor of 4, the resistance of the wire decreases by a factor of 4. The factors affecting the resistance of a metal wire. Different metals. Wires of the same length and cross-sectional area but made of different metals will have different resistances. Wires made of copper and aluminium will have low resistances. Resistance, voltage, and current. The resistance of a circuit component can be calculated by using the equation resistance equals voltage divided by current. If the voltage is measured in volts and the current is measured in amperes, then the resistance will be measured in ohms. Electric current. An electric current is a flow of charged particles through a material. In a metal, these charged particles are electrons. All metals contain free electrons that allow a current to flow. Some materials conduct by a flow of charged positive and negative ions. These materials are called electrolytes. Electrolytes. In an electrolyte, the current is carried by a flow of positive and negative ions. Positive ions will flow towards the negative terminal or cathode. In the above example, positive lead ions are attracted to the negative cathode. Negative ions will flow towards the positive terminal or anode. Here, negative bromide ions are attracted to the positive anode. The charge carried by the moving particles is measured in coulombs. The quantity of charge carried by a current in a given time can be calculated using the equation charge equals current multiplied by time. Here the current is measured in amperes and the time in seconds. Energy changes in electric circuits. The battery acts as a store of chemical energy. Inside the battery, chemical reactions occur that convert stored chemical energy into electrical energy. The battery supplies an electric current to the circuit. This current carries the electrical energy to the circuit devices. Each device performs an energy change. The lamp converts electrical energy into heat and light. The buzzer converts electrical energy into sound. The motor converts electrical energy into kinetic energy. Heat energy. When a current flows through a resistor, the electrical energy is converted into heat energy. The greater the resistance, the greater the heat produced for a given current. Many electrical appliances operate using the heat generated in a resistance. Calculating electrical power. The power of an electrical device is the electrical energy it converts into other forms in 1 second. Electrical power is either measured in joules per second or watts. We can calculate the power of an electrical device by using the equation electrical power equals voltage times current. Electric circuits. The components present in an electric circuit can be represented by a circuit diagram. Circuit diagrams do not use three-dimensional pictures of the components. Instead, each component has its own unique circuit symbol. This makes circuit diagrams quicker and easier to draw. Series circuits. In a series circuit, each component is connected one after another. The same current flows through each component. Each bulb is equally bright. Each receives the same energy per second from the current. The energy provided by the battery per second is shared equally between both lamps. The current in the circuit is, however, only 1/2 of that obtained with a single bulb. The two bulbs in series glow much less brightly than a single bulb. A variable resistor can be used to control the current in the circuit. If the resistance is increased, less current flows and the bulb glows less brightly. Parallel circuits. In a parallel circuit, the components are connected side by side. Each bulb now glows at the same brightness as a single bulb. The current drawn from the battery has doubled so that each bulb glows at its normal brightness. If we place ammeters into the circuit, we can see that the current divides equally through both lamps. The circuit behaves as though the bulbs are acting independently of one another. Potential difference. In series circuits, the sum of the voltages across each component is equal to the supply voltage. Here, the sum of the voltages across each lamp equals the supply of 6 volts. Notice that these lamps are not identical. In a parallel circuit, there will be the same voltage across each component. Here, each lamp has a supply voltage of 6 volts across them. Both will glow with equal brightness. When resistors are connected in series, the total resistance of the circuit increases and the current flowing falls. The total resistance of a circuit is equal to the sum of all the resistances connected in the circuit. In this final circuit, the total resistance is 10 ohms. Resistance, parallel circuits. When resistors are connected in parallel, the total resistance of the circuit decreases and the current flowing rises. The total resistance of two resistors connected in parallel can be calculated from the equation 1 divided by resistance total equals 1 divided by resistance 1 plus 1 divided by resistance 2. Here the total resistance of the circuit is 1.2 ohms. The current flowing in the circuit has now risen to 5 amps. Potential difference. The potential difference, or voltage across a component, is the energy transformed when 1 coulomb of charge flows through it. A 6-volt battery converts 6 joules of chemical energy into electrical energy as 1 coulomb of charge passes through it. Each coulomb of charge leaving the battery carries 6 joules of electrical energy. 2 joules of electrical energy are converted into heat and light as the 1 coulomb of charge passes through lamp 1. The voltage across lamp 1 is 2 volts, or 2 joules per coulomb. 4 joules of electrical energy are converted into heat and light as the 1 coulomb of charge passes through lamp 2. The voltage across lamp 2 is 4 volts, or 4 joules per coulomb. Each time a coulomb of charge passes through the battery, it gains 6 joules of electrical energy. This 6 joules is delivered by the coulomb of charge to both the lamps in the circuit. Calculating electrical energy delivered. The electrical energy delivered to a circuit component can be calculated from the equation energy delivered equals potential difference times charge. Quick quiz. If 120 coulombs of charge pass through the lamp on the left, the energy delivered to the lamp on the right is 120 watts, 240 joules, 120 joules.